Okay, two things. First of all, in homework I assign this and says that except for the last problem, which you have to put some thinking. And the second half of your homework is actually old examples. So I'm giving you some practice from old exams. But when I ask you to derive inequalities that must be satisfied, you just have to derive I1, I2, I3. Maybe do the cases if it's immediately easy, but I'm not asking you to do all the work I did with tau I. So for your homework assignment, you don't have to do all the work I did for tau I. Adam, 7 grades. Okay. No, it's not a very long homework. Except for the first part, which is the CSTR game, that will take some time. But the non-CSTR is basically all from all the exams, so they're fast. The last problem will require some thinking.
Is that also from a non-exam?
Yes. All right, but I want you to see the utility of this. I want you to say that here we have specific inequalities. This here gives me guidance for KC, this here gives me guidance for tau I. Okay? And the reason why I got the 1/7 thing is because open loop unstable. If it was open loop stable, it would have been 0, would have been a bound. Because it's open loop unstable, 1/7 is the lowest bound. You need to have some control to be able to stabilize it. If KC, yeah. You should have figured out conceptually that it couldn't have stayed like that, because for KC equals 0, what do we have? Open loop, right? If you put KC equals 0, U equals U0. And the system is open loop unstable. Putting KC equals 0 makes it open loop at the nominal steady state. So clearly KC will not go epsilon close to 0. And the real lower bound is 1/7. So the final result here would have been 1/7 less than KC less than 299/7. And tau I by this inequality. And then anything you pick that satisfies this for those forms of stability. Now, I have been emphasizing that if you make an algebra mistake, you're going to probably get 0 partial credit in the problem.
What? Wait.
You haven't been here, I think I've already mentioned it a few times. If you mess up the sign of k in your transfer function,
Oh, okay.
you're going to get no partial credit in all likelihood. Why is that so important? I've seen you've also seen in all the tuning rules, we have k equals something kc, so automatically has the same sign. And the sign k is what? K is typically the transfer function at s equals 0. So remember, g of 0 is the process gain. But steady state gain applies only when you have stability, right? So sine of Kc. If open loop stable, sine of Kc must always equal sine of K, which is sine of GU of 0. What's the sine of GU of 0 in this example?
GU0 negative.
It's negative, right?
Yeah.
Here is GU, you put s equals 0, what do you get?
What's e to the negative something? Positive? I don't
At
know.
s equals 0, what's e to the whatever?
Oh, 0. Oh, 1.
1. So it's minus 7, right? G of 0 is minus 7.
Can you put the board up?
So for the stable, sine of kc, sine of k is sine of G of 0. If open loop unstable, with one positive pole, sine of kc would be equal to minus sine of G U. So in this case, that's why kc had to be positive. In this case, I have one positive pole.
Is KC not a term that's for closed loop systems?
Yes.
For open loop systems?
Yes. The sign of kc for the closed loop system depends on the open loop GU. If the open loop GU of 0, if the open loop GU is stable, the sign of kc should be the same as the sign of GU 0. If it's unstable with one positive pole, it should be opposite sign. What about if it's unstable with more than two positive poles? In all likelihood, as a matter of fact, I don't think you find any KC that will make it stable. So, if you have open loop unstable with two positive poles, it's basically abandoned hope. Okay, you cannot stabilize such a system. So, clear everyone? So that's why I'm not writing any case if you have more than one open loop positive poles. But I don't know of any physical situation where you have more than one open loop positive poles. Clear everyone? So that's why in this case we found that KC had to be positive, even though GU of 0 is negative. If I had done this example, and I'm not going to do this, with a plus 1 here, that condition would have become KC. Well, then GU of 0 would have been positive, right? So if I had a plus 1 here, KC would have to be positive. Okay? Okay. Hunter, okay? Mika? All right. So that's what I wanted to say about the Ruth theorem. After the break, we're going to move to a new chapter, frequency response. Remember, I wrote down 4 criteria for stability, 4 methods for checking stability of a closed loop system. The first one, direct calculation, is just numerical methods, nothing specific, I can tell you. Just write the characteristic equation, try numerically to find complex roots of that, and good luck. Okay? Second method is the Ruth theorem. Third and fourth methods, we're going by the name, Bode stability criterion and Nyquist stability criterion. Both of them are cases of frequency response. Until now, we have been doing input changes that were step changes where the input was going to a new steady state. If you make a step change and the system is stable, it will go to a new steady state. But what if your input instead is a periodic function, a sine or a cosine? If your input is a sine and a cosine, or a cosine, the output will never reach a steady state. Instead, if we have stability, it will reach a periodic solution, a repeating periodic solution. And frequency response, that depends, what you get, depends on the frequency of the input sine or cosine. So frequency response refers to what happens to the output as I change the frequency of the input sine cosine. Clear? And that's going to be the basis of the Bode and the Nyquist stability criteria. I do have an open question mark. I cannot really afford to take the time to do the proof of the Nyquist stability criteria. That would take a couple of lectures. If anybody has taken a course in complex variables, probably you're covering that there. But normally I do a semi-proof of the Bode stability criterion, but I think in interest of time, since I'm a little bit behind and I don't want to go over the speed limit on new concepts, I will skip that semi-proof. It's in the notes though, it's in the class notes. So I will skip something that is in the class notes. And I will show you though, without proving the Nyquist stability criterion, how we get the Bode stability criterion as a consequence of the Nyquist stability criterion. We can consider the Bode stability criterion as a special case of the Nyquist stability criterion. Basically, Bode stability criterion, it's a little bit easier to see things on graphs, but it's requiring open loop stability. Nyquist stability criterion does not require open loop stability. It has no constraints. We can always use the Nyquist stability criterion. All right, let's take our break, and we'll continue with frequency response after. Let me see if I have time.